Okay, class. So this time, let's discuss about the periodic table as well as the placement of this electronic configuration, the placement of elements based on the electronic configuration. So from here, take note that we have the metals for the green part. For the green part, we have the non-metals. Take note, these are the non-metals, including the hydrogen. And then the metalloids are on the blue line, okay, on the blue zigzag line. So these are the metalloids, and the rest are metals. So the white as well as this color orange are metals. So once we define metals, these are the elements that can easily give up electrons. While non-metals, these are elements that can easily accept electron or gain electron. And once we say metalloids, they have a shared characteristics between metals and non-metals. Now, take note also that I highlighted here the uranium. The uranium is the last naturally occurring element. So that is the element that can be found naturally on Earth. It is not made from the laboratory, or it is not synthesized from atomic laboratory. So after uranium, that means 92 and above. So that is 93 up to 118. Those are called transuranium element. So these are elements that are artificially prepared. That is why it is called as transuranium or after uranium. So let's try now to identify the placement of these elements in the periodic table. So remember that this will gonna be our pattern. This one will be the S blocks. This one will be the P blocks. So this will gonna end in P. So if you do the electronic configuration, the element here we're gonna end in P, while the elements here we're gonna end in S. And we have the D blocks, and we have the F blocks. Note also that the maximum electron for S would be 2, right? So this one we're gonna end in S1, this one we're gonna end in S2. For the P, the maximum electron is 6. So we're gonna have P1, P2, P3, P4, P5, and P6. And likewise for the D, we're gonna end it in D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. And for the F blocks, it will gonna end in it will gonna have a maximum of electron of 14. And so we're gonna have here F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F12, F13, and F14. And then we're gonna study that deeper as we proceed on the video. Now, let me just discuss the S blocks as well as the P blocks. The S blocks and P blocks, these are known as representative elements. Okay? So again, the S blocks are known as the representative elements. So those are going to end in S and those are going to end in P. And that's what we're going to study for today's video. So let's just recall the Aufbau principle when we do the electronic configuration, wherein we're going to have here the 1s, 2s, then followed by 2p, then 3s, 3p, 4s, 3d, 4p, 5s, and then 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5x, 5f, 6d, and 7p. So this is how we're going to arrange the electronic configuration, or filling up of the electrons in the electronic configuration. Okay, let's first go now with the group 1A, or better, this one is called as NS1. Observe the lithium, the ending of lithium, the sodium, potassium, as well as the rubidium. Observe that carefully. And observe the ending of electronic configuration. Now, the valence shell is the main energy level. Look at the valence shell. So the valence shell of lithium would be 2, the valence shell of sodium would be 3, potassium would be 4, and rubidium would be 5. And note that the valence electron or VE, it means the electrons in the valence shell. And they are all going to end in one, right? So meaning to say one in electron, one in S sublevel. And if we're going to count now, let's count for the lithium. 1, 2. Look at the position now of the lithium. The lithium is in period 2. Period. Sodium is in period 3. Look at the ending. Potassium would be in period 4. Rubidium would be on period 5. And I bet you're going to guess on the cesium. Cesium would be 6s1. And what could be the ending for francium? So let's try first to observe the cesium. If you're going to look at the cesium, the electronic configuration is here. That would be atomic number of 55, and it will going to end in 6s1. Okay? Next, francium, which is 7s1. 7s1, if you're going to do the electronic configuration, that would be for francium 87, and that would be end in 7s1. So if you're going to count for cesium, that would be 1, 2, 3, 4, 5, 6. That is on the 6th period or 6th horizontal alignment. And for the francium, that would be for the 7th period. Okay? Now, Group 1A or Group 1 are known as alkali metals. It ends in the electronic configuration of Ns1. These are known as alkaline metals. They are extremely reactive that this element should be stored in oil. And the usual charge of this is 1 positive, meaning to say these metals could easily give up 1 electron. The S1 can be given up as 1 electron. Meaning to say 1 positive, it could be lost, right? It could be given to another element. So the group or families of alkaline metals, I think these are the most familiar one. We have the lithium, sodium, potassium, and rubidium. So we have here Ns1, where N, it means the main energy level or the period number. And when we're going to make it as an ion, we have it like lithium positive. So this is how you write the lithium ion, the sodium ion, potassium ion, and the rubidium ion. Okay, so once there's a term ion, meaning to say there's a charge. So the common charge of these alkaline metals are 1 positive. Next, let's go now with the group 2A. And look carefully the pattern for the 2A or the group 2 or Ns2. If the beryllium atomic number is 4, so if you're going to do the electronic configuration, they're going to end up in 2s2. Same with magnesium, 3s2, 4s2, for strontium, which is 38 in atomic number, it will going to have an ending of 5s2. Carefully count the strontium. 1, start here, 1, 2, 3, 4, 5. And so the ending would be 5s2. Note that the valence electron of this group 2A is 2. Now, how about the barium? Can you guess what would be the ending of barium? I guess you'll be right. That would be 6s2. And so if we're going to do the electronic configuration of barium, that would be 6s2. And how about for the radium? Radium would be 7s2. Let's do the electronic configuration. That would be now the electronic configuration of radium. If you count for the radium, 1, 2, 3, 4, 5, 6, 7. Now, group 2A or group 2 is known as alkaline earth metals. It ends in this electronic configuration of Ns2, known as alkaline earth metals. Yes, they are active, but not extremely as reactive as group 1A, but of course, they are still reactive. And the usual charge is 2 positive, meaning to say they're going to have to give up the 2 electrons. And so here are the most common alkaline earth metals for the Ns2: beryllium, magnesium, calcium, strontium, and barium. And then we're going to do the ion. We call this as beryllium ion, magnesium ion, calcium ion, strontium ion, and barium ion. There is a word ion if you're going to have a 2 positive. And then let's jump on group 3A, on the P blocks. Let's jump here for the aluminum group or the boron group. For the boron, we have Z equals to 5, and look at the ending, Ns2 and P1. So 2 plus 1, that would be 3A, right? So here, for the aluminum, 2 plus 1, that would be 3. Same also for the gallium, it will gonna end up with 4s2 for P1. Once we do the electronic configuration, well, we have here 3d10, but the highest main energy level would be 4. So we're gonna have 4s2 and 4p1. And then indium, which is 49, this we're gonna end up in 5s2, 5p1. So meaning to say, this 3a, we're gonna end up in p1. Okay, it becomes 3a, that would be 2 plus 1. Notice the difference. So the valence electron here is 3. Why? 2 plus 1, that would be 3. The valence electrons in the highest main energy level. And here, the ending of this would be 6s2, 6p1 for the thulium. Let's try to get the electronic configuration, if that would be true. And this is now the electronic configuration of the thulium. 6s2, and then the 6p1. The highest main energy level would be 6. And so the group 3A, known as boron group, boron is the first metalloid. Aluminum and downward elements are metals. And the usual charge of these metals are 3 positive. So we have here the aluminum ion. Okay, you call this as aluminum ion. Next, carbon group. Same pattern for the carbon group. 2s2, 2p2, 3s2, 3p2, 4s2, 4p2. So 4a, we're going to end up in p2. And then 5s2, 5p2. Notice that the valence electron is 4 because when you add these 2 electrons, that would going to be 4. Now, can you guess what would be the ending of lead? If the ending that comes in your mind is 6s2 and 6p2, then you are right. Let's try to do the electronic configuration. This one will be the electronic configuration of lead, which has an electron of 82. Let's move further. This time, the group 4A is known as carbon group. Carbon is the first non-metal. Silicon and germanium is a metalloid. Tin and lead are heavy metals, and the usual charge is 4 positive or negative. Note here that the charge is 4 positive and negative, meaning to say elements on this could have a useful charge. It could gonna have a positive electrons, meaning to say 4 electrons would be removed or 4 electrons would gonna accept. And that is why carbon and silicon is more on non-metals. They are more on sharing of electrons, and we're gonna study that on our next discussion. Okay, but well, note that the carbon is non-metal, sharing of electrons. Silicon and germanium is metalloid, while tin and lead is a metal. And that is why the usual charge of tin would be tin for positive, and once you have a lead ion, that would be lead for positive. Okay, but of course there would be another possible charges for tin and lead. Let's go now with the nitrogen group and look at the pattern. I hope you can see now the pattern why the valence electron would be 5. So these are the nitrogen, phosphorus, and arsenic. Now take note that aside from writing the long electronic configuration, we have here a shortcut electronic configuration. Instead of writing it like a very long one, look at the arsenic. And before arsenic, we have here the 3p6, that is the electronic configuration of argon. So instead of writing the long electronic configuration, I would rather write here the argon and then continue now from the 3p6, continue for the 4s2, 3d10, and 4p3. This is called as the shorthand notation. Same with the antimony. This is the shorthand notation, wherein the 4p6 from 1s2 to 4p6, that would be the electronic configuration of krypton. And so take note that we're going to add the valence electron, that would be 5. And I think that's the reason why it's called as group 5A or group 15 in IUPAC naming. So guess what would be the ending of bismuth? That would be 6s2 and 6p3. Let's look at the electronic configuration of bismuth. 6s2, 4f14, 5d10, 6p3. But of course, we're going to get the electrons in the highest energy level. And I hope that you are now seeing the pattern. This one is the shortcut for the bismuth, shortcut way of writing it. Next, note that the nitrogen and phosphorus is non-metal, arsenic and antimony is a metalloid, bismuth downwards are metals. And the usual charge of this is 3 negative. Why 3 negative? Why we start now for 3 negative? Take note of the ending of the elements. I want you to take note, class, on the ending of these elements. Now, for the P here, it lacks 3 electrons for the P to be complete. So instead of giving up the 3 electrons, it will gonna gain electron. And that is why it has 3 negative for nitrogen and phosphorus. Meaning to say, they will gonna accept 3 electrons for the P to be complete. And once we do it as an ion, the nitrogen ion, the N3 negative, and that is called as nitride. If N is nitrogen, N3 negative, that is called as nitride. And we have P3 negative, meaning to say it will be an ion where we're going to add up 3 electrons. You're going to call that as phosphide. Next pattern would be for the 6A for the oxygen group. And I want you to closely look at the patterns for oxygen, sulfur, selenium, and tellurium. So we have here 4s2, 4p4, 5s2, 5p4, 3s2, 3p4, and 2s2, 2p4. Note the valence shell and the valence electron. And guess what would be the ending of polonium? If your answer would be 6s2, 6p2, then you are right. So if you count for the polonium, 1, 2, 3, 4, 5, and 6. And let's do the electronic configuration for polonium. That would be 6s2 and 6p4. Okay? The ending of this is ns2 and p4, and group 6 is known as the oxygen group or the chalcogen group. Chalco means ore, so gen means genesis, and that is why they are called as ore former, which wherein these elements can be usually found in rocks. For example, sulfur can be found in rocks. Oxygen usually reacts in rocks, or oxygen usually reacts in metals. That is why we have rust, right? So these elements usually react in ore. So we have here the oxygen, sulfur, and selenium, and the usual charge here is 2 negative. And I'll bet you're gonna know the reason why is it 2 negative or negative 2, simply because the P sublevel, it lacks 2 electrons to for it to be completed. Okay, can I just edit this one? NS2 and P4. Okay, I'll try to edit this one, NS2 and P4. Okay, and that is why 2 negative. Okay, and then we're gonna do the O2 negative, meaning to say it adds up 2 electrons. You call that, if this one is called as oxygen, we call this as oxide. S2 negative, we're gonna call this as sulfide. And Se2 negative, we're gonna call that as selenide. Next would be the group 7A or the group 17, which is NS2 and P5. So here, look at the pattern. Same pattern. For the bromine and iodine, I'll just write the shorthand method. And look at the valence electrons. Once you add them, that would gonna be 7. And so we're gonna have 6s2 and 6p5. Let's look now at the astatine electronic configuration, 6s2 and 6p5. So the ending of this electron configuration is ns2 and p5. They are known as halogens. Halo, it means light. So these elements usually a component for making lamps. That's why you keep on hearing halogen lamps, the one that's being used in court, right? So we have halogen lamp, we have the chlorine lamp, okay? We have the iodine lamp. So these are light formers. Halo means light, gen means genesis. And so the usual element here would be fluorine, chlorine, bromine, and iodine. And the usual charge is 1 negative. Why? NS2 and P5, right? Let me just edit this. So this one again is P4. And so we're going to have here NS2 and P5. And this one will be 1 negative. And F negative 1, that is called as fluoride. Chlorine, this is called as chlorine, but Cl negative 1, that is called as chloride. Bromide and iodide for the negative charges. And then the last one, that would be the group 18, NS2 and P6. Of course, the helium is Z equals to 2, so there's an exception, that is 1s2. But for the rest, neon, argon, krypton, and xenon, they were going to end up in 2s2 to P6. And so look, they are complete, right? So the valence electron is 8. And the radon would be 6s2 and 6p6. Let's try to do the electronic configuration of radon. That would be 6s2 and 6p6 here, although we're going to have 4f14 and 5d10 in between, but we are getting only the valence electron. Okay? And so these are known as group 8A or noble gas. Noble, in English word, noble, it means like you're a rich person. You don't need someone. Okay? And they're now called as noble gas because these gas are non-reactive. It seems that they don't react, or sometimes they are called as inert or inactive elements. They're also called as lazy elements, and that is why since they don't react, they usually exist as gas. And then we have here the helium, neon, argon, krypton, xenon, and radon. And take note that the useful charge of this element is 0 because they have completely filled d orbital, meaning to say they are octet filled except for helium, of course, which is duet. And so here, I think it's now already complete. But let me just change this to NP4. Okay. So our representative elements now are complete. So these are A elements, or these are S blocks and P blocks. Let's try to have some practice. So here we're talking about the S blocks, and here we're going to have the P blocks. Let's try to identify the ending of X. That would be 2s1, right? Why? ns1, the ending here would be ns1. So the ending would be here would be 2s1. How about the w? If you're gonna count 1, 2, 3, 4. So the ending would be 4s2. Next, how about the y? The y ending would be, how about the z? Let's try to look at the z. Okay, y. Y would be 3s2 and 3p4. Y, 1, 2, 3, right? So we're gonna have a third main energy level, P1, P2, P3, P4. So it will gonna end up in 3s2, 3p4. And 2 plus 4, these are in group 6A. How about the Z? What do you think will be the ending for Z? The ending will be, if you guess 2s2, 2p5, then you are correct. How about the G? 1, 2, 3, 4. So if you are guessing that would end in 4s2 and 4p6, that would gonna be correct. Okay? And so that would be the summary of the characteristics or placement of this electronic configuration to the periodic table. Note, we have the D blocks and we have special rule for D blocks. Okay, I'm gonna cut the video for now because we're gonna have a separate discussion for the D blocks. And there's a special rule for D blocks, as well, of course, for F blocks.